work energy theorem is W net equals delta KE, means the net work done on an object equals to the change of the object's kinetic energy. So this theorem is called work energy theorem, derived directly from the Newton's second law. And then we look at it if there's any other possibility to get another version. And then first of all, we need to understand the net work done can be calculated using F net multiply the displacement, which is S here, then multiply the cos theta, the angle between the vector force and the vector displacement. The problem is the F net must be constant to use this formula. And then there's another alternative way to calculate the network. If we calculate the work done by each force, so we call it WF1, WF2, WF3, and so on, add them up, that also can be treated as network. Okay, and based on this understanding, we separate the work done by the net force into two categories. One is the work done by the conservative forces, and one is the work done by non-conservative forces. And if we assume there is only one conservative force, which is Fg, actually that's the case in this course. We only study the conservative force Fg. So then we just replace the W conservative force with the WFG, and then we also know that WFG equals to negative delta GPE is equals to the negative change of gravitational potential energy. So then we move this term to the other side. So eventually we got WNC equals delta KE plus delta GPE. So it means the work done by non-conservative forces equals to the change of KE plus the change of GPE. And also the kinetic energy plus the gravitational potential energy, and together we call it mechanical energy. And of course, be aware that I only assume there's only one conservative force, otherwise it should be KE plus PE. Right, and if there's only one conservative force, Fg, and then we can just use GPE to represent all the potential energy. But anyway, the mechanical energy is the sum of kinetic energy and the potential energy. And then this version 2 can be written as a simpler form. Work done by non-conservative force equals the change of mechanical energy. So yeah, that's the version 2. And then version 3. Version 3 is actually just an exception of the version 2. So what if the non-conservative force does zero work? So they either does not exist or they just does zero work. So if this one equals 0, you can see the equation becomes the delta ME equals 0. Or if you separate the delta ME into ME final minus ME initial, and then move the ME initial to the other side, we should get ME initial equals ME final. Okay, now this I prefer use this idea because it's easier to understand. Saying if there's no non-conservative forces doing work, so we simply have the total mechanical energy equals to the total mechanical energy final. So this is initial, this is final. So that's why it's also called a conservation of mechanical energy. Now don't forget, conservation of mechanical energy, there's a condition is there's no non-conservative force doing work. Okay, for example, if there's no friction and no extra external force acting on the system, and then we can see the object's total mechanical energy is conserved. And of course we can separate the ME into KE and GPE, so we can have this idea total the sum of the KE plus the GPE at the initial position equals to the sum of the kinetic energy plus the GPE at the final position. Okay, so that concludes the idea about two versions derived from the original work energy theorem.